about the complex that we have chosen, which is the Biscurcuminpalladium 2 aqua. So if you ever wonder how the complex is written in formula, well, the formula of this complex is written as this, which is the PD is the palladium, CuRCH is the ligand, which is the curcumin, and the counter ion, which is H2O. As you can see here, the complex is inside the bracket and the counter ion is outside bracket. So the structure of this complex is this, where you can see the central metal, which is the palladium, is bonded with two curcumin. And the curcumin, the donor atom of the curcumin is oxygen, where the oxygen acts as donor atom or an atom which donates electron to the central metal. So next, we're going to determine the coordination number for palladium. It is obvious that we can see from here the coordination number is for Y because from the ligand, which is curcumin, we can see that there are 4 bonds from the ligand bonded to the central metal. So you can see that the coordination number is 4. So how about the geometry shape of this complex? Well, if the coordination number is 4, we can say that the geometry shape of this whole complex is tetrahedral. Why? Because curcumin ligand is also known as a binding ligand because, one curcumin ligand, they tend to donate 2 pairs of electrons to the central metal. As you can see here, one curcumin donate 2 pairs of electrons from 2 oxygen. So this whole complex has a charge of 0 because when you see the counter ion, which is aqua, it has no charge. So next, if you want to see the oxidation state of palladium, we calculate by PD plus 2 ligand, the charge of ligand. Well, the charge of curcumin is -1, so we have 2 curcumin, so we times by 2 equal to the charge of the whole complex, which is 0. And then the palladium, the oxidation state of palladium, we get plus 2. And the final one is we can compute that palladium PD2. Next, we're going to determine the stability of this whole complex based on effective atomic number or EAN. First, we look at the central metal, which is palladium, and we have to determine the atomic number of palladium based on the periodic table. As we can see here, based on the periodic table, we can say that the atomic number of palladium at ground state is 46. And next is the metal ion, which is the central metal ion for this complex. As we calculated earlier, the charge for the palladium in this complex is 2+, so the atomic number would be 44. Next is the ligand, which is the curcumin ligand, has a charge of -1. And as we know, the donor atom of curcumin is oxygen, and every 1 oxygen atom will donate 2 pairs of electrons. So there is 4 oxygen in the complex, so 4 times 2 electrons would be 8 electrons. So the addition of these 2 will get 52 electrons. We can say that this complex does not obey EAN rule because the total number of electrons is not the same as any noble gas in the periodic table.
Hello, Assalamualaikum everyone. My name is Aisha. So I will discuss about the electronic transition in this palladium complex. Electronic transition involved in Biscurcuminpalladium 2 aqua. From this graph, we can see that there are 2 UV visible spectrum. The red color is for the complex and the black color is for the curcumin, which is the ligand in the complex. There are 2 higher peaks shown by the UV spectrum of the ligand, which are at 261 and 417 Nm. On the other hand, there are 4 peaks in ultraviolet region shown by the complex. 417 Nm is the highest peak of the ligand, which indicates that the transition group is pi to pi star transition. Pi to pi star transition have shifted to slightly higher energy is an indicative of involvement carbonyl group in the curcumin. Absorption at 1621 cm-1 is correspond to the carbonyl group. In the IR spectrum of the complex, the peak due to C double bond O was found to be shifted towards lower wave numbers. Thus, it is possible to ascertain that the coordination of oxygen from carbonyl group attached to the metal. Hi, I'm Mimina Ziha. So I'm going to explain about the visible spectrum of this complex. Actually, transition metal do have color because it absorbs light at specific wavelength in the visible region of electromagnetic spectrum. This from this graph, the highest peak of the wavelength of this complex is 430 nanometer. 430 nanometer is in the range of violet color. The absorbed visible light of Biscurcuminpalladium 2 aqua is violet. So, we can see the color of this complex from the complement of violet color, which is yellow. Complement of violet color, which is yellow, on this transition metal complex. So, my group has chosen the crystal field theory to explain about the complexes. Do you know what is the crystal field theory? So, let me introduce you a little bit about crystal field theory. As you know, this theory is developed by Hans Pels and John Hesbrook van Vleck. Crystal field theory, or CFT, describes the breaking of orbital degeneracy in transition metal complexes due to the presence of ligands. CFT describes the interaction between a transition metal and ligands arises from the attraction between the positively charged metal cation and the negative charge of the non-bonding electrons of the ligand. Based on the strength of the metal-ligand bonds, the energy of the system is altered. This may lead to a change in magnetic properties, color, and hydration energies of transition metal complexes. Okay, same as VVT, CFT also have few assumptions. So first, the assumption about CFT is metal ion at the center. So here we can see this is metal ion at the center, which is positively charged. The second assumption is ligands are treated as point charge. So here we can see have 6 ligands, which is all the ligands are negatively charged. The third assumption about CFT is bonding occurs through metal and ligand electrostatic attraction. The electrostatic attraction is present due to the metal and ligand, which is different charge. Fourth, which is bonding is purely ionic. For the fifth assumption is metal and ligands repel each other, and the last one, the d orbital degeneracy, is broken as ligands approach. Degenerates mean having the same quantum energy level. Here is this 5 orientation of the d orbital, which is super important in this crystal field theory. For the first d orbital orientation, we can see is dx2 minus y2. So we can see the lobes lie on the x and y axis. For the second orientation is dz2. So for the dz2 have some speciality, which is the loop is parallel to each other. So for the third orientation is dyz. dyz, the lobes is lie between the y and z axis. For dxz, the lobe is lie between x and z axis. For the last one, which is the dxy, the lobe is lie between x and y axis. There are 2 splitting of d orbital, which is in octahedral and tetrahedral of ligands. So my friend will explain to you about the splitting of d orbitals in tetrahedral field of ligands.
Assalamualaikum and hi, my name is Nur Nabila binti Muhammad Zaini, and now I will continue about the crystal field theory, CFT. To complete this diagram, we need to answer this question first. The first one, we need to determine the shape of the complex. Okay. This is the structure of that complex. So, this shape is a tetrahedral shape. What is the oxidation state of metal center? So, when we do calculation, we will get the metal center have a positive 2 charge. Number 3, we also need to determine the d electron configurations of the metal center, where PD have 46 electron. So, this is the ground state electron, a positive 2 charge. So, the d orbital have 8 electron. Number 4, determine whether the splitting energy is greater than the pairing energy and also the strength of the ligand. To fill the electron in the d orbitals, it depends on splitting energy and the pairing energy. Usually, square planar and tetrahedral complex have the splitting energy always large. Then, electrons tend to be paired because pairing energy is much less than splitting energy. Therefore, square planar and tetrahedral complex are usually have low spin. When the splitting energy is higher than the pairing energy, so the electron arrangement, it will pair up in the lower energy d subshell first. Now we can complete this diagram where this metal have a positive 2 charge. So its condensed electron is Kr equal to 4 d8. It have d8. 1, 2, 3, 4, 5, 6, 7, 8. It have d8 over here, and here also we need to have 8. In order to answer at this part, we already know that splitting energy is higher than pairing energy. So the electron pair up in the lower first, then at here. So we pair at here first, the balance, and we will put at here. So 4, 5, 6, 7, 8. Or we have complete this diagram for the crystal field theory. Okay.
It have 2 unpaired electrons, so it is the paramagnetic.
I hope you understand. That's all from me. Thank you.